Everyone today knows how to hold a world map. North is at the top, south is at the bottom, east is on the right and west is on the left. Intuitively, we also feel that north is at the top and south is at the bottom. The terms north, south, east and west are obviously borrowed from Nordic mythology, where Nordri, Sudri, Ostri and Vestri are the four dwarfs that support the sky. It is interesting that in Old High German, the word Norden also means below. It seems that there was a time when the north was perceived as below and the south as above. When we speak of the north today, we mean a point where the north comes together at a pole. This is due to the coordinate system of a globe that is in use today. In ancient mythologies, north was a direction in a region, in an area, and not a pole with a center. Some old maps from the Middle Ages show large land masses with mountain ranges and four large rivers at the North Pole. Hyperborea is a mythical land beyond the north wind. A black magnetic mountain, the Rupes Negra, is said to be located in the center of the land. This country was often depicted as paradisiacal, eternally spring-like and inhabited by happy people. In contrast, Norse mythology tells of Niflheim, a cold, foggy world of ice and cold. Ultima Thule or Avalon are further sagas, while Asgard and Shambhala describe a spiritual realm. The strong association of these places with the north is mainly found in pagan European culture. The concept of a geographic North Pole has shrunk the sagas and realms of ancient mythologies into a single point. On today's world maps, the land masses have disappeared and there is no land at the North Pole on Google Earth either. It is just a point where the compass points to. The compass, it is said, comes from China, although the magnetic properties of magnetite have been known for a long time. According to the official story, it was somehow brought to Europe by crusaders and used as a secret weapon. When this order was broken up, the compass also became more widely known. So much for the story. The needle of a compass itself is a magnetic North Pole. Since it points to the North Pole is technically actually a South Pole, and the South Pole is in fact the North Pole. Since the two poles are reversed, experts use terms such as Arctic or Antarctic magnetic pole. The Chinese were right all along when they named their compass the needle that points south. Imaginative people also associate this fact with a possible pole reversal. The idea of a bird high up in the air with a view of the earth has long captured the imagination of people. To this day, aerial photography is still a great source of fascination, and since such shots have so far required extensive equipment, especially for high altitudes, the public is dependent on images from official sources such as NASA. World maps are an expression of this bird's-eye view, and they are still a matter for a few well-known large institutes and organizations. It is not possible for the average person to produce world maps with their own resources or even to check the existing ones using data they have measured themselves. A landscape seen from above only appears directly straight down, at a right angle to the earth as it is. The further you look outwards, flattening the angle, the more the landscape distorts itself. This is due to our perspective perception. This is a problem when you want to map a landscape or even an entire country. You have to display every point on the map as if you were directly above it. This is an almost impossible task, even with airplanes. Even on Google Earth, you can see the distortions when streets or buildings have not been photographed exactly from above. Only when everything is in focus are the proportions and also the lengths and widths of the respective objects correct. In peripheral vision, there are always distortions. To create a map that is true to scale, you would have to scan every single square meter from above at a right angle to it and at a relatively small distance to determine the actual size. Since the focus is always only one point, inaccuracies are still to be expected even then. An exact measurement is only possible with a measuring rod lying horizontally on the ground. Everything else is calculation, and miscalculations are always possible. To determine points on the Earth's surface, a spherical coordinate system is used throughout today. Longitude and latitude are one method of determining positions on a sphere, whereby the general rule is that on a globe the horizontal lines represent the latitude and the vertical lines the longitude. The coordinates themselves are each given with a latitude and a longitude. Only modern technology allows us to measure exact distances over shorter distances. Longer distances have to be calculated by calculating the distance between two coordinates on a globe with a certain radius. Of course, there are also problems with surveying terrain, because even an altimeter cannot accurately indicate the actual height due to the system. All that can be measured are very small sections of the Earth. The rest, together with the oceans, is calculated using coordinates that have been determined at various locations on the Earth based on the position of constellations and the Sun. Even today, large areas on the continents of South America, Asia and Australia have not been accurately surveyed. Today, radar and laser technology are used to carry out land surveys. At sea, things are much more difficult. Without electronics, the ship itself cannot determine its exact position if it has no fixed reference points, is floating on an unpredictable current, and wind and weather prevent accurate speed measurements. In bad weather or fog, navigation is almost impossible, leaving only the compass, the foghorn, and sailors to sound the depth of the sea with a plumb line. Navigation before the advent of radar was very difficult and more of a game of chance than precise mathematics. The latitude could be determined fairly accurately centuries before the longitude, because the Sun is highest at the equator and the latitude is easy to measure. Based on the position of the Sun at 12 noon and the date, it is easy to calculate the latitude and how far north or south of the equator you are. At sea, determining the exact longitude to know where you were west or east of the equator was long an unsolvable problem, with seafaring countries offering prizes worth an entire warship for a solution. All that was available were compasses, star charts, and protractors to measure the positions of the stars, sun, and moon. Atmospheric lensing and the movement of the ship made it even more difficult to determine the exact position. The inaccuracies were so glaring that the Spanish Armada lost dozens of ships near Ireland on the way back in 1588. And the English fleet lost 4 warships at once to the rocky shores of the Isle of Scilly off southern England for the same reason in 1707. These are just 2 examples of many. It was only from 1773 that reliable clocks were available that could be used to determine a distance travelled based on time and speed. Only then did you know where you were if you maintained the direction with the compass and knew the starting point. If a watch was even just 1 minute fast or slow, it meant that you had a quarter-degree deviation on the chart. At the equator, a quarter-degree is about 17 nautical miles, and that could be extremely dangerous for ships. If you sail west with a compass, the helmsman is forced to constantly adjust the course to the right in order to stay on the same latitude. Only a route due north or due south theoretically requires no course corrections. This can be seen on a polar projection such as the Gleason map, where the latitudes are shown as circles and the compass points north from the centre. Navigating at sea is and was a demanding task, even though today almost all shipping traffic uses electronic systems to follow safe trade routes. Navigating in unknown waters without modern equipment was then and still is a high risk, and testifies to the daring of the crews who set out on long, dangerous expeditions far from home. But it also shows that old sailing ships, which themselves had massive difficulties with navigation, could not just measure an entire continent so quickly. The earliest surviving maps are said to include cave paintings and etchings on Tuscan stone, followed by extensive maps created by ancient Babylon, Greece and Rome, China and India. What is amazing is that some maps give the impression of being drawn from a view from above, with the respective distortions in the periphery. More recent maps from the Middle Ages are incredibly detailed works of art. Among all these different artifacts from the past, we must not forget the fake maps and writings that circulate among collectors. The story of the painter Wolfgang Beltracchi has shown how art forgers can dupe highly respected experts with their works. Anything can be faked, and in such a way that even the world's best experts are deceived. In this respect, there is a certain doubt about every old map. Old maps are ideal for asserting historical territorial claims or fabricating heroes and myths. There are enough examples of old maps and old writings turning up at exactly the right moment. There seems to be a gap of about 1,000 years in the mainstream chronology of cartography, because more detailed maps were only created in the Middle Ages, although if we are to believe the historians, the knowledge for this existed 1,000 years earlier. Seafaring before this time apparently managed almost without nautical charts. The sky is also a map of its own, on which the positions of coasts and places on Earth can be found in the various constellations. A long-lost knowledge of ancient times. The maps from the Middle Ages almost look like those of today, although we are always told how dark, primitive and backward everything was back then. If you look at the map drawn by the Flemish cartographer Gerhard Mercator in 1569, it's hard to imagine. Or the map by Hermanus Venrade from 1531, which also shows Antarctica. And yet, Antarctica was supposedly only discovered in the 19th century. What is particularly remarkable is that these maps show very accurate longitudes, which was hardly possible in the Middle Ages. It seems as if people knew more back then than they are willing to admit today. With regard to technical developments such as navigation and cartography, a few conclusions can be drawn. In the Middle Ages, 3 supposedly completely independent map traditions emerged. Firstly, there were the Mappae Mundi. These maps were religious representations that were not intended to provide an exact map of the world in a scientific sense. Then there were the Portolan charts, which were originally books or maps with navigational information such as landmarks, lighthouses, currents and port conditions. The map of Piri Reis and the Carte Pisan of 1291 are examples of such Portolan charts. They are remarkably accurate. The Piri Reis map itself contains many mysteries. It shows the coast of America and part of Antarctica with a land course with perspective distortions in the peripheral areas. The land itself, however, is hidden under meter-thick layers of ice and cannot be seen from a ship. Serious scientists avoid the map because everything would point to highly developed technology that should not have been available at the time. The map is dated 1513, but it was not rediscovered until 1929. In line with the political situation in Turkey at the time and the depressed mood among the people, a previously unknown hero in the form of an admiral was just what was needed. In the 14th century, a Greek manuscript of the Geography of Claudius Ptolemy, said to be over 1,000 years old, made its way from Constantinople to Italy, where it was translated into Latin. Ptolemy himself had only drawn a few rough sketches, but his work contains written instructions and extensive tables for creating maps on a spherical shape. The maps created on this basis, world maps and numerous detailed maps, are called Ptolemy maps. So little is known about Ptolemy himself, but the writings of this unknown person are said to have been hidden somewhere for about 1,300 years until they were rediscovered, purely by chance, around 1400. As if there had been no interest in cartography for 1,300 years. Whoever believes that. At the time when Ptolemy's writings appeared, many more ancient writings were rediscovered, of course quite by accident, and the theories they contained were taken up as if people had been waiting for them. It is strange that for these foundations and numbers, Greeks are always sought with their names, places of residence, and dates of birth and death, even though historical chronology was not introduced until the 17th century. It is also striking that the works are only preserved in fragments which were handed down in medieval manuscripts and later editions. Significantly, these are all copies, transcriptions of these ancient writings, including incorrect translations. The originals cannot be found and verification is impossible. Calculating with triangles, rectangles, spheres, and other geometric shapes cannot have been lost on official historians either, because the buildings of the Egyptians, Sumerians, and other early civilizations everywhere bear witness to advanced knowledge of geometry. But if it is about justifying a heliocentric or philosophical worldview, then the Greeks are the basis on which the whole structure of thought is built. In the context of critical chronology, it can be assumed that many figures of antiquity are pure inventions in order to be able to ascribe existing writings and also new or falsified writings to an author. This antiquity may have existed, but it is to be found in the much more recent past. In the medieval writings copied by Ptolemy, there were thus theories about a geocentric worldview in which the earth stands still and the universe revolves around the earth. Just like Aristotle, who is also a dubious historical figure, Ptolemy assumed that the earth must have a spherical shape. Once upon a time, a Greek by the name of Hipparchus divided the earth into lines of longitude and latitude, and another time Eratosthenes is given as the originator. No one really knows for sure. The Greek by the name of Eratosthenes is said to have worked out the circumference of the earth, and it is also claimed that he calculated the relatively exact distance to the sun. But there is a problem. There is no way to measure the earth's radius or the distance to the sun directly. You have to calculate. But there is a problem there too. To calculate the earth's radius, you have to know the distance to the sun, and to calculate the distance to the sun, you have to know the earth's radius, an actually insoluble dilemma. On a flat plane, you can calculate the distance to the sun by triangulating it using the methods of another Greek named Aristarchus. Aristarchus, for his part, assumed that the crescent moon is at right angles to the sun, and that the sun itself must be very far away. He solved the distance to the sun purely mathematically with an angle based on experiments. However, according to today's standard science, this estimate was fundamentally wrong. Eratosthenes' method of measuring the angle of incidence of the sun's rays at the same time at distant locations could also have occurred to Aristarchus. A triangulation of the sun thus yields around 5,000 kilometers on a flat plane without curvature. It is said that Eratosthenes assumed that the sun's rays were parallel because of Aristarchus' calculations, because the sun was supposed to be far away. Anyone looking at this picture here, and everyone has seen it before, may wonder how anyone can come to the conclusion that the sun's rays arrive on Earth in parallel. Eratosthenes was not able to measure the curvature of the Earth himself, no matter what he wanted to calculate the circumference of the Earth or the distance to the sun. He needed an exact diameter of the Earth, so he estimated the diameter, just like that. In any case, official science claims that he was able to determine the circumference of the Earth to an astonishing accuracy of 98%. Today, it is believed that the Earth has been completely measured, but this is not the case. All information about the circumference and the distance to the sun is based on calculations, and even today, there is not a single piece of information about how the diameter of the Earth is determined exactly. All that can be found are various self-referencing calculations. In the end, it remains an estimate, and everything else is based on it. Ptolemy is said to have described this spherical coordinate system, and suddenly all cartographers drew maps with it. It is striking that Albrecht Dürer refers to Ptolemy on his 1515 star map of the hemisphere. On the map itself, globes of the starry sky can be seen. The scientific justification for a spherical Earth was probably that ships disappear over the horizon. but by the late 16th century it would have been possible to use a Kepler telescope or a Galileo glass to determine that this is not the case. You can see further with binoculars than the curvature of the Earth would allow. So now, at the end of the 15th century, Christopher Columbus comes along and thinks he will find a way to India by sailing in the other direction across the open sea to the west. After all, he knows that Ptolemy described the Earth as a sphere, and Eratosthenes provided the appropriate radius. Or did he? Was Eratosthenes even known at the time? We don't know the details. If he had calculated the size of the Earth using Eratosthenes' radius, and compared it with the already mapped land masses, he would have noticed that there was a huge empty space between Spain and India, and that his provisions would not have been sufficient. The fact that Columbus had calculated a new, smaller Earth radius was not known at the time. Columbus is said to have discovered the Bahamas before America in 1492 and the Greater Antilles in 1504. And just 34 years later, in 1538, cartographer Giraldus Mercator drew the outlines of America with remarkable accuracy on his first world map. And in 1569 he drew a map by hand that almost looks like it was printed by a computer. Mercator, the Belgian, whose real name was Gerard de Cremer, had adopted the Latin name Mercator, which means merchant or trader. He used it to create the famous Mercator world map for navigation at sea, which is said to have shaped a new era of trade, a heyday of the merchant trade, and a new view of the world in the Middle Ages. A map whose type of representation was given the name Mercator projection, and which is still used today, and is familiar to most people as a map of the Earth. He is said to have worked on the map for years, and the engraving in wood or copper for printing also took time. The details of the continent of America are amazing. It took 34 years to measure the coastlines, and 30 years later the rivers and towns of North and South America in detail, collect the coordinates and draw a map. A huge area, a huge amount of data, and an immense logistical effort. Cruising along foreign coasts in unknown waters was largely a matter of luck, and with the sailing ships of the time and the primitive means of navigation, it was difficult enough as it was. But to survey it all so precisely without being able to determine the longitude exactly is almost a miracle. That sounds just as incredible as the story of a few hundred Spaniards conquering an Aztec empire in no time. The biggest rivals, Spain and Portugal, maintained colonies in parts of Asia and Africa, founded new settlements in America, and fought various wars during this time. One may wonder where the many people came from who were needed to maintain agriculture, a war industry, the construction and maintenance of colonies, the recruitment of soldiers and the ship's crews for trade, the army and expeditions. In addition, an army of agricultural workers, construction workers, dockers, miners, etc., and a whole host of personnel for the organization. Finding reliable astronomers and navigators was an additional difficult task. A single Spanish galleon alone required a crew of up to 150 men. Portugal, with only about 1.2 million inhabitants at the time, and Spain, with about 7 million, are said to have divided up the whole world in the Middle Ages, a world whose total population at that time is said to have been about 450 million people, and who then gathered all this data from the warring naval powers, translated, sorted and classified it so that Mercator could draw his map in a Sisyphean task, nobody knows. Well, Columbus might have never existed, and it could all have been quite different. The world map of Giraldus Mercator from 1569 and the surveying technology of the time are a contradiction. In the context of chronicle criticism, this whole story about Ptolemy, Durer, Mercator and the discovery of America is peppered with many question marks, and probably these stories and the maps themselves come from the late 18th century, and the story of Columbus is invented. What really happened is written in the stars. However, we should abandon the notion that the Middle Ages were primitive in any way. The intellectual, creative and character qualities of people and their view of the world were different back then. We are the ones today who find ourselves at the end of a continuous civilizational and intellectual decline, despite smartphones, the internet and electric cars, or perhaps precisely because of them. Now we have the Mercator world map, a cylindrical pole map projection with enormous distortions. A projection is a map grid design, also known as a map projection or map illustration. It is a method in cartography used to transfer a curved surface of the three-dimensional sphere to a flat two-dimensional map or other three-dimensional geometric body. The general rule for map projections is that the horizontal lines represent the latitude and the vertical lines the longitude. And so this Mercator projection is not true to scale, the land masses are distorted. It is used mainly for navigation at sea, and has served well in this area because it was possible to draw straight lines that would otherwise be curved on a sphere. In contrast to other continents, Europe and Greenland appear disproportionately large on the map, while Africa appears smaller than it really is. It is still used in classrooms today. Maps represent a world view. In a psychological sense, people today perceive what is at the top as more important than what is at the bottom. Over time, various map projections have been developed that use the spherical projection as a basis to represent the land masses in different proportions in two- and three-dimensional forms. Maps are usually two-dimensional and must always be converted from the three-dimensional globe projection as a basis. Today, there are various projections, such as the already mentioned conformal Mercator projection, the equal area Gaull-Peters projection, the square flat map that is true to length, the angular triple projection that mediates between the conformal and equal area projections, and thanks to modern computing capacity, around 400 other different projections. The Mercator projection or the flat representation of the Earth in a two-dimensional polar coordinate system are just two of many projections, and all show the same thing but in a different way. Today, we can assume that the data regarding land masses is reasonably accurate. Individual projections serve various purposes in air and water navigation, for the road network, wind maps, weather maps, and much more. It is noticeable that there are no country roads on the land masses on nautical charts, that nothing in the sea is shown on land maps, and that distances are always given in only one direction. Each map has its own specific purpose, and each one looks different. There is the Gleason's projection with a polar coordinate system, which many refer to as a flat Earth map. This map, however, is a converted projection based on the common spherical coordinate system. An incredible piece of work, considering that in 1892 computers did not yet exist. It is a map that was calculated according to the position of the sun at 12 noon at the respective location and is intended for calculating times. Here too the size of the land masses is optically distorted due to the given coordinate system. In the center, the land masses are squashed together and pulled apart towards the outside. The Gleason projection is not a map of the flat Earth, even though a flat Earth would explain a lot. On a flat Earth, the land masses would look different. If you look at a globe with lines of longitude and latitude marked on it, you will notice that the lines form small trapezoidal areas due to the curvature. This is due to the coordinate system. If you change the coordinate system, the proportions of the land mass change without changing the size itself. As a general rule, horizontal red lines on a map projection represent latitude, and vertical red lines represent longitude. When these lines intersect, they form limited areas. The areas of each projection cover the same area of the Earth as the corresponding areas on the other projections, only in different proportions. The limited areas influence the shape of the continent in which they are contained. Despite the differences, these are the same land masses. Here are several different projections of Africa. The shape of the continent and the angles at the shoreline change. This is due to the coordinate system. If the bounded area is mostly wide rectangles, then Africa will be squatty and wide. If the area is mostly tall, skinny rectangles, then Africa will be tall and skinny. If the areas containing West Africa are smaller than those containing Central and East Africa, then West Africa will be noticeably squashed more. The same thing happens with the other continents. The eastern edge of South America can be either pointed or flat depending on the coordinate system. On the left is a cylindrical coordinate system, where the top line is the North Pole and the bottom line is the South. Most people are most familiar with the cylindrical map projections. On the right is a polar coordinate system, where the center point is the North Pole and the outermost circle is the South Pole. We can switch between the coordinate systems and convert the cylinder coordinates. The upper line, the North Pole of the cylinder coordinates, becomes the center point in the polar coordinate system. The lower line, the South in the cylinder coordinate system, becomes the outermost circle in the polar coordinate system. The conversion also works in reverse. These conversions are easy to do in any image editing program like Photoshop or GIMP. The UN and other world organizations use a polar projection of the globe in their logo. Whether you want to interpret this as a reference to a flat Earth is up to you. The famous Captain James Cook noted in his logbook on his journey along the Antarctic ice wall that his ship was making only slow progress and that he repeatedly had to struggle with navigation problems. He covered almost 60,000 nautical miles, a distance that is much too large for a continent of Antarctica. Even today, radar systems have problems at the poles. While the coordinate system seems to work reasonably well for the northern hemisphere, in the southern hemisphere, ships are observed to travel more slowly than usual. This is explained by strong countercurrents. This claim becomes problematic when ships travel slower in both directions west and east at the same southern latitude, and that seems to be the case. This suggests that the distances are actually greater than shown on the map. In addition, when navigating with a compass, you are more likely to find yourself on the wrong route near the poles. Something is still wrong with the maps in the southern hemisphere. Many a sailor explains this with the missing North Star, which can no longer be seen from there and thus makes navigation a lot more difficult because you have to calculate a lot more. But even around 1800, there were problems because, despite their precise clocks and sophisticated ship compasses, which still worked even in heavy seas, seafarers repeatedly made navigation mistakes. Even in the northern hemisphere, navigation on the high seas was a craft, an art form that required a lot of experience. For example, you would follow the compass to due north on the chart to arrive at a certain port, but each time you would hit the coast a few nautical miles to the south and then have to travel north along it to reach the port of destination. Even if you couldn't explain it by the currents, it seemed as if some places were not where they should be on the map. Experienced captains often corrected the ship's routes based on their gut feeling. Every Boy Scout who reads a map with a compass knows that when calculating a longitude, he still has to use an additional table, a table of magnetic declination. Declination is an important sounding technical term for deviation. What is meant is a magnetic deviation. It is important to know that the Earth has two north poles. One is geographical, on which the coordinate system is based, and the other is magnetic, which is determined by the Earth's magnetic field and is where the compass needle points. The geographical and magnetic north poles are not at the same location, and so corrections to the geographical grid system are necessary when using a compass. In practice, this means that the compass points north somehow, but to use the maps, you have to add or subtract the declination in degrees, which is given in tables or on the map, depending on your location, so that the direction on the map is correct. This can sometimes involve deviations of 180 degrees. Believe it or not, when the compass points north, you have to go due south in the opposite direction. As early as 1600, people in Europe knew that the Earth has a kind of magnetic field that aligns the compass needle to the north. But it was only in 1832 that the German Carl Friedrich Gauss built the first geophysical observatory in Göttingen and constructed a sensitive magnetometer for it. With this, research ships were sent all over the world, and the magnetic field was measured as accurately as possible. Further international measurement campaigns took place in 1882, 1932, and during the International Geophysical Year 1957-1958. It was only in 1884 that the first International Earth Survey Conference was held in Washington, D.C., at which the definition of the zero meridian and the degree of latitude was established. Magnetometers are used to measure the strength and direction of the magnetic field and its deviation from a calculated north-south axis in existing world maps. This made it possible to create tables that could be used to calculate the deviations to the west or east in order to arrive at the correct location on the world and nautical charts. That is, the magnetic deviations were adjusted to match the nautical charts. Whether anyone ever considered that the land masses on world and nautical charts might be incorrectly proportioned and positioned is not known. On the one hand, we know that on the high seas there are frequent and unnoticed changes in course due to wind and currents. On the other hand, doubting the Royal Nautical Charts would have cost many a captain his job. If you went off course, the magnetic field was to blame. Officially, it is announced that the magnetic pole is moving and that the constantly changing deviation between the geographic North Pole and the Arctic magnetic pole makes it necessary to regularly adjust the conversion for navigation aids, such as maps and radio beacons for the purposes of navigation. The magnetic North Pole moves only slightly in relation to the entire surface of the Earth and the geographical grid. In addition, even the geographical North Pole is by no means stationary and is also supposed to move. So officially, both the magnetic and geographical North Poles are moving, with hair-raising justifications that will not be discussed further here. A particular region in the southern hemisphere has been known since 1950 as the South Atlantic anomaly. This is a weakness in the Earth's magnetic field that affects satellites and spacecraft flying through this zone, it is said, and that requires special precautions for navigation. The magnetic declination graphics provided by the relevant organizations show extremely confusing magnetic field structures that technically do not make any sense. All over the Earth, especially near the poles, unexplainable abnormal swirls in the magnetic field can be found, and in such a way that the U.S. Department of Commerce was moved to the following sentence in a coastal and geodetic survey report from 1964. People would probably be much less interested in magnetic poles if they realized that their position does not determine which way a compass needle points. So, we have a geomagnetic field that behaves mysteriously and that apparently cannot be relied upon. If we believe these declination maps or tables, then the Earth's magnetic field is a complete mess, especially at the poles, and yet, for centuries, compasses have been used successfully at sea to get from one port to the next. Many a sailor of old would be surprised to hear that his compass is actually useless. So there is the old Mercator world map, which was created for ship navigation without the possibility of taking precise measurements over larger areas. They sailed around the world with the help of the compass and discovered America, and created maps with surprisingly accurate longitude information. There was only one North Pole, namely the magnetic one. It was only much later that it was discovered that the magnetic and geographic North Pole are two different things. The geographic grid in Mercator's time was viewed from the magnetic North Pole, and then, a few hundred years later, it was discovered that there is an Earth's magnetic field that is supposed to have a massive influence on navigation with the compass. Nevertheless, the measurements made previously with a compass and without declination tables still serve as the basis for existing map material. And so the modern world maps do not look much different from the old Mercator map from 1569. At the latest, since the measurements of the Earth's magnetic field, it should have been noticed that something is wrong with the maps, or with the spherical coordinate system. But nothing of the sort. They separated the North Pole into a magnetic and a geographic pole and claimed that both are not fixed and everything was fine again. And then you find world maps where the proportions of the land masses are not quite clear. Consistent in the details, but something is wrong on a large scale. If you measure the width of the USA on the map and then calculate the driving distance, it is only 15% more than the width on the map. This is a road that covers thousands of kilometers over mountains and all kinds of winding terrain. Then there is a coordinate system that itself poses problems. On a sphere the land masses are curved. On a straight surface the same land masses would be stretched apart. If measured on a flat plane, then on a sphere the surfaces are compressed at the poles and stretched at the equator. Today, the Earth is officially no longer a sphere, but rather pear-shaped. And measuring a pear is a completely different story, especially when using a spherical coordinate system. And then you find anomalies in the magnetic field in the southern hemisphere, problems with navigation and slower ships that indicate that the distances are longer than measured on the maps. The explanation for the recently discovered South Atlantic anomaly is that the Van Allen belt is said to be close to the Earth at this point, and the Earth, which is now said to be no longer round and symmetrical, is to blame for this. Even today, it is not possible for a person who enjoys traveling to get to the North or South Pole alone to check out the claims made about them. If you set out to go north or south with a compass, you will eventually be stopped by the military and have to realize that you need all kinds of permits, proof, and above all, money to access these polar regions. And if you then look at time zones on these maps, you will see a pattern that cannot be explained logically either. In addition, extensive laser, light and mirror measurements over the past 10 years have shown that the Earth has no measurable curvature above water. Modern cameras are used to photograph mountains that should be behind the horizon according to calculations. With the official curvature of the Earth, these should not be visible. Particularly impressive are infrared camera images that show long distances without curvature. Infrared light has the property of bending less upwards. You can see mountains that would have to be hidden behind the curvature on a sphere. All these indications lead one to suspect that declination does not exist at all, but that the land masses are distributed quite differently than they are shown on the usual maps, and one corrects these false proportions, positions and inclinations using declination tables. One could also say that one uses a model that does not correspond to reality, but that one adapts it to reality using a trick. All this points to a mistake by Eratosthenes in estimating the diameter of the Earth. If there is no curvature on the Earth, then there is no diameter to estimate. In this case, the Earth is obviously not a sphere, but a flat plane. And then the Sun has a measured distance of about 5,000 kilometers. But what would the Earth look like in this case? Since the two poles are offset at the north, to remove the declination, the magnetic North Pole would have to be placed on the geographic pole with its own grid, and the land areas of the geographic grid would have to be used. The geographic pole is shown by the red dot at the top. The magnetic pole with its own coordinate system is represented by the center of the concentric latitudes. When the magnetic pole and its coordinate system are set to the geographic pole, a waveform is introduced during the conversion. This corresponds to the distance between the magnetic North Pole and the geographic North Pole on Earth. In this coordinate system, the coordinate system of the magnetic pole is shifted to the geographic pole. This changes the proportions. You can see the latitudinal waveform in the converted cylinder projection. Even in the more exotic coordinate systems, the surfaces cover the same areas of the Earth and have the same land masses. The equality between the coordinate systems can be verified by manipulating the bounded regions into the same shape. To convert A to B, first the polar coordinate system A is converted to a cylindrical coordinate system, A1, and the polar coordinate system B is converted to a cylindrical coordinate system, B1. B1 has squares for each bounded area, so all bounded areas of A1 must be converted to squares when converting. The irregularly bounded surfaces of A1 are converted into regular squares in A2. The equality of A2 and B1 is thus confirmed. America has increased in size, Africa has shrunk slightly, South America and Australia have moved to the right, Europe has moved to the left, all in line with the straightening of the zigzag lines of longitude. Converting A2 back to polar also confirms the equality of the original B-polar projection. This is what a flat Earth would look like using the magnetic North Pole as the origin and ignoring declination. All of this goes to show that we know very little about what the Earth really looks like. Declination tables were adjusted to match maps and charts, and the Earth was made slightly pear-shaped, all to create a consistency that navigators at sea and in the air could work with. In short, navigating with a compass today is a patchwork of calculations that require modern electronics. It is amazing how seafarers manage to find a port overseas at all. Here you can see how the magnetic declination changed over time, while the map of the world below remains the same. It should be the other way around. The magnetic field always remains the same, the compass always points north, but the positions and proportions of the land masses would have to be adjusted to the magnetic field. We have the measurements based on spherical coordinates, but since it obviously cannot be a sphere unless it were many times larger, another shape must represent the Earth as it really is, slightly curved or flat, whereby physics, with the known behavior of liquids, tends to favor a flat variant. The behavior of a gyroscope in an airplane or the transmission of microwaves over long distances are just two more of many confirming indications. A simple Earth-based triangulation of the Sun on a flat plane results in a distance of just 5,000 kilometers between the Sun and the Earth, but the Earth had to be a sphere and the Sun very far away. The distance to the Sun and the diameter of the Earth can only be estimated, and here we have made a fundamental mistake. Thus, a simple error in a basic assumption can be incorporated into calculations and change an entire world view. There are too many inconsistencies involved for it to be a simple mistake. In today's model of the globe, everything depends on reference points, and if a fundamental reference point such as the radius of the Earth is not correct, then the whole model is not correct. If the original assumption that the Earth is a sphere is not correct, that does not mean that a mathematical construct cannot be built on it that compensates for miscalculations by means of tricks. Today, no one does manual positioning anymore. The whole world relies on electronics and systems such as differential GPS and software that can easily compensate for these inconsistencies. Incidentally, the abbreviation GPS originally stood for Ground Positioning System. Only later did it become known as the Global Positioning System. In the Middle Ages, maps had to be drawn purely according to the compass. They knew nothing of the Earth's magnetic field, nor of the deviation from the geographical grid. With a compass that points upwards everywhere and without magnetic declination, many land masses, coastlines and ports are in different places and further apart, and on a flat surface the distances near Antarctica are much greater. Land masses on this map have different proportions and face north differently. The concept of magnetic declination is one way to compensate for map errors that occur when using the wrong spherical coordinate model. If you put a grid on the magnetic North Pole, move that pole to the geographic pole and then create a polar projection, the Earth looks a little different than we know it. Without declination, adapted to the compass and the land masses in the correct proportions and positions. But unfortunately there is no way to confirm this unequivocally. Or maybe there is? When we look at the sky, there is something else. Even the largest ground-based objects such as mountains and skyscrapers shrink and disappear at distances of several dozen kilometers. In fact, only two objects are visible from any location on the Earth's surface, the Sun and the Moon. The Sun is a source, a locus, if you will, a blinding light that is more or less featureless. The Moon, on the other hand, has recognizable constant characteristic features on its surface. Another characteristic feature of the Moon is its phases, from waxing to waning and back again, an eternal cycle. We will focus here on the waxing crescent and the features on this side of the Moon. What we find is an undeniable reality. An interesting thing happens when you reflect the Moon. First, an unsharp mask filter is applied to make the dark areas a little darker and the light areas a little lighter. Finally, we create the coordinate system based on magnetic north. Let's go back to our cylinder transformation to convert our polar image of the Moon into a cylindrical image. Continental boundaries are marked and the coordinate system is superimposed on it. The land is colored green and the water blue. Do you see the pattern? America is on the right, Europe is at the top left, Australia is at the bottom center. All the coordinates match measurements on Earth. Is this the real view of our Earth? An image reflected on the Moon? There are also anomalies that have not been included in the outlines of the land masses. Let's take a closer look at this. To start with, an unmanipulated image of the Moon. Then the exact continental outlines are determined. There are these anomalies in the lunar image, to which no outlines for land masses are assigned. Each of these anomalies is present in relief maps of the Earth, which show the elevated areas underwater. Here East Asia, China, Korea, and the area of the Yellow Sea in Japan. When you separate the light from the dark, the shape of the land below is revealed. Japan and Korea are immediately recognizable, and the corresponding latitudes and longitudes. South of Japan is an area with several long land arms, clearly visible on the Moon and on relief maps. And southeast of this area, between Australia and America, is the largest anomaly on the map. Relief maps show that this is East Oceania, i.e. Micronesia, Melanesia, and Polynesia. Over 10,000 islands scattered over tens of millions of square miles of ocean east of South America. The southern coast of Brazil is the Rio Grande Plateau, or Rio Grande Rise, clearly visible on relief maps. 200 to 400 kilometers west of the coast of southwestern Malabar coast of India are the Lakshadweep Islands, which are clearly visible on relief maps. 700 kilometers south of that, along the Chagos Lakadai Ridge, are the Maldives. East of that is the 90th East Ridge, which unsurprisingly is at the 90th eastern longitude. Off the west coast of northern Namibia in Africa is the Walvis Ridge. Between South Africa and Madagascar is the Mozambique Ridge. To sum up, not only are all the continents visible on the Moon and in line with the given latitudes and longitudes, but all the major ocean ridges on world relief maps are also present and consistent. Is this the true view of the Earth, our home? It almost seems as if this map on the Moon shows the Earth with a much lower water level of the oceans than today. And if you look closely, you can still find land masses at the North Pole and other places. Land that is not shown on modern world maps. Only two objects are visible from every location on Earth. And the only object with recognizable features reflects every location on Earth. This is no coincidence.